this is what we are doing in this first class and maybe the first couple of classes, right? So the recording of this class is going to be put right here. So the first thing that we're going to do is look over some of the basic skills in maths that we are going to tackle, right? So add maths prerequisite, right? So the first basic thing that you're going to have to know, right? And remember, this document is in the Google Classroom, so you should go and download it and get it and work with it. You will have homework to do, right? But this is one of the things that you have to know, and that is your sets of numbers. So Sydney, would you say that you remember these sets of numbers that I have here? Kinda, yeah. You're really gonna need to know these things just real quick. Your natural numbers are the counting numbers. So they just start from 1, 2, 3, dot, 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 to infinity, right? The whole numbers are basically all of your natural numbers, but with a 0. So 0 is not a natural number, but it is a whole number. So you really have to remember these little things. They are important, right? Integers, which is the Z, right, is, you see you have the 0 here. So you have all of the whole numbers. And then from the 1, you have all of the natural numbers. But then you have negative numbers as well. So integers is all of it. So you can see here that you have natural numbers, 1, 2, 3. And natural numbers, all of natural numbers could be found inside of your whole numbers. So this would be your whole numbers. All of natural numbers is inside of there, but then you have 0, which is not a natural number. These are your natural numbers, right? Then we have integers. And inside of integers, you can see we have all of the whole numbers and all of the natural numbers. So whole numbers, natural numbers are all inside of integers, yeah? But the integers, we also have negative numbers. -1, -2, -3, -4, all of that stuff. And you know how to draw this diagram, because I actually have this diagram a little better over here, so you'll see it over here, right? And then we have rational numbers. Now, what are rational numbers? Rational numbers are integers. So you can see all of the integers are inside of rational numbers, right? But a rational number are integers where you have like two integers, like p and q, but you have p over q. So we're talking about fractions here. So I can have one integer over another integer. So this is what we refer to as a rational number. So this is not a whole number. It's not a natural number. It's not integer, but it does have integers. It does contain integers. So all of these are rational numbers. So you have like things like 2 over 3 and that kind of thing. Right? Sydney, I lost you so far?
No.
You get lost already?
No.
All right, so you're okay so far, right? Things gonna get a little bit heavy, but in this class, we had to get down to business, right? So that is where all of the circles go. After irrational numbers, no, after rational numbers, sorry, come the I. The I is for irrational numbers. Irrational numbers are numbers that are irrational. They're not inside of this set. They are over here on this side. Irrational numbers have to do with things that we don't know the value of. Things like the square root of 2. If you punch the square root of 2 in a calculator, is a recurring decimal that goes to infinity, you know, or things like pi. Yeah, we don't know the correct value of pi. The decimals go to infinity, right? So those numbers where the decimals are going to infinity, we could never really know the true value of those numbers. So they are called irrational numbers. And yeah, the irrational, we could never really know them. But then you have real numbers. Real numbers in set theory, real numbers is like your universal set. So you know your universal set, you just draw it as a rectangle. And you could see you have your real numbers here, right? But then We do have some other numbers. We will see these numbers very, very briefly in this curriculum. These numbers will usually, you'll have to deal with this in A-level maths. So A-level maths is where we talk about these two numbers here. But we might see them briefly in this curriculum, but we wouldn't have to deal with them. And those are imaginary numbers. Imaginary numbers do not exist. Yeah, imagine that. But we could do maths with them, right? So an imaginary number is I. I is equal to the square root of -1. You could never have the square root of a negative number. You could never have it. Right? It's impossible. So I doesn't exist. However, if I square both sides of this equation, I'll have I squared is equal to -1. Well, -1 does exist. And so I could have something here that represents -1. Yeah. So this is the kind of madness that we just get to in maths. And it's a bit mad, and complex numbers are just kind of like expressions that use imaginary numbers, that use I. So we'll have an expression A plus BI, where I is imaginary. Yeah. So these are the sets of numbers. These two, we will see them a little bit, but not much. You just use them mostly in A-level maths. Right? But you do have to know these. Let me know. And of course, this is the Venn diagram we was just talking about there. So you can see all of the natural numbers, 1, 2, 3, are inside of the whole numbers, which have 0 in it. And then all of that is inside of the integers, which include the negative numbers. And all of that are inside of the rational numbers, which include fractions containing integers. Right? And all of that are inside of your real numbers, which is basically everything else. You're seeing irrational numbers here, but look, complex numbers just kind of cover everything too. So now we're seeing that the Venn diagram has changed a little bit, where the real numbers are not the universal set anymore. We're expanding the universe now. Complex numbers are the universal set because they include imaginary stuff, right? Now we're gonna talk about a very, very basic topic. And you can see I have tons of questions, and you all are going to have to do lots and lots of questions, right? But what I will do is I will just do the first couple from each page, and you guys are gonna have to do the rest. It's all up to you. Yeah, it's about practice, practice, practice. Now the first thing we're gonna do are directed numbers, and you can see we have something called polynomials here. And since we're talking about polynomials is one word, right? Is one word. But poly means many, and nomial means numbers. So many numbers. So is any expression that contains a x plus a y minus a q, is equal to z. This is an expression, this is an equation that has many numbers in it, many unknown numbers. And so this is a polynomial. And so we're going to have to learn how to deal with polynomial expressions. But before we learn how to deal with polynomial expressions, right? And I don't know if I should erase that yet. I'll leave that on the board there for now. Before we learn to deal with polynomial expressions, we had to go back to SCA. And we're going to talk over here about the rules for directed numbers. So the rules for directed numbers, we just refresh in and I'll see. Now, Shreya, Joseph, and Sarah, you guys are in my math class. You guys should know these rules. Sydney, you was never in my math class, so I don't know if you learned the rules the way we did. We just do things a little bit different here. Right? But directed numbers is these kind of things, right? So if you have, like, say, -4 plus 3, or, you have -5 minus 2, them kind of things. So these are directed numbers, right? But we're going to see exactly this. We're going to see this kind of stuff a lot, and you had to be able to deal with this a lot. So if it is you're bad at directed numbers, you're going to have problems here, right? Because we're going to be seeing these directed numbers with X and with Y and with things, with stuff. Yeah, and so we can't let them things, them X's and Y's, we can't let those things scare us, because it's just normal directed numbers. So let's see if we could remember the rules for directed numbers, right? So what are the rules for directed numbers? Sarah, you could remember? For addition and subtraction, we had to talk about. We're talking about on this page, we're going to talk about addition and subtraction of directed numbers, right? So we're talking about addition and subtraction. All right, so let me give you the examples. We have -3 minus 4. Where's this?
-7.
-7. And we have 3 plus 4. Where's this?
4. 7.
Dinosaur, right? What do you notice about both of these questions? The signs are what?
Different. No, the same, but the answer.
Yeah. No. Just the signs are the same. Yeah. So Sydney, take a look at this. The 3 is negative and the 4 is negative, right? In this case, the 3 is positive and the 4 is positive. Sydney, you recognize that, right?
Mm-hmm.
All right. So in this case, the signs are the same. So when you have the same signs, what do you do, Sarah?
And keep the signs.
When you have the same, if you see -3 minus 4 and you're wondering what to do, when you have the same signs, you add and you add, comma, and keep the sign. You add and you keep the sign. So -3 minus 4, they have the same signs. So I'll add 3 and 4 is 7, and I have that negative sign there. You add and you keep the signs, right? So you can see 3 and 4 is 7. They're both positive, so there's a positive 7 there. So Sydney, do you understand this simple little directed number stuff? This form 1 stuff, right?
Mm-hmm.
All right. So what about this one? Let me see how good you are, Sydney, right? So we saw that the signs are the same, but what if the signs are different? So what if I had -4 plus 3? What if the signs are different here? What will I end up with? Why will I end up with a negative here? Where's the answer here? You could feel free to be wrong, by the way. Where you say I'm not hearing you properly? Wait, is negative what? Ah, very good, very good. I'm glad that you make that mistake, though. It's not -7, right? But I'm glad that you make that mistake because it's showing.
-1.
All right, yes, very good. All right, so -1. Right? The -7 is an easy mistake to make, though, but that is the reason why we're going over this. I know it might seem boring and be like, oh God, why are we doing this again? But that is the reason why, because we can't make them kind of mistakes in maths, right? So you can see the signs are different here. So what do we do? Shreya, you remember what's the rule when the signs are different?
We find the difference and keep the sign of the larger number.
Yes. So when the signs are different, what do? You find the difference. So you see, my math students know these rules very good, right? You find the difference. So the difference between 3 and 4 is 1, but you keep the sign of the larger number. The larger number is the 4, so we're going to keep the sign of that 4, which is a negative, right? So you keep the sign of the larger number. And of course, this works the same with X, right? This works the same with X. Now, this is the rules for addition and subtraction. We are going to do the rules for multiplication and division over here. But these are rules for addition and subtraction. Before we get to these questions, there are a couple of other notes that we should take. what we're going to talk about here is just another very simple form one thing, and that is called the associative law. And well, Joseph, you don't have a microphone, but could you type in the chat what you think or you remember the associative law to be? All right. So if I have something like that, right? So the associative law is telling us, because a lot of the times we are going to want to go minus 3 plus 4 is minus 1, minus 7 is minus 8. When we do things like that, we could make mistakes. We could make simple, careless mistakes. But the associative law says that we could add or subtract in any order as long as we keep the sign. Keep the sign. So for example, right, I could see here that, all right, negative 3 minus 7. The signs are the same. So that means that I could add these. I could add any numbers I want. I don't have to add it in an order. I could add it in any order as long as I keep the sign. So negative 3 minus 7 is, the signs are the same. So I'll add it and I'll keep the sign, right? Negative 3 minus 7 is negative 10. So I could cross off that. That is make a negative 10. But then I have this negative 10 and this plus 10. So plus 10 minus 10, well, that will cancel and give you 0. Yeah. And then I could see that I have, well, 4 plus 5. 4 plus 5 is 9. So this 4 plus this 5 is 9. Yeah, but then you have this 9, and then we have a minus 9 here. So 9 minus 9 will give me 0. And the answer here is 0. Okay? So this is what the associative law is about, that you can add and subtract in any order as long as we keep the signs. So you can see here that in AddMaths, you're going to be dealing with polynomials, which is x, y, z, p, q. And in these polynomials, you're going to meet directed numbers, those kind of situations. You're going to meet situations where you have to use the associative law. So you need to know that you can add things in any order. And we will see that just now, right? Just now. And the last thing I just want to talk about here is just the basics of polynomials. The basics of polynomials, right? So we're talking about polynomials, the basics. And the basics of polynomials, well, let me just look at some examples. That is the best thing, right? So let me see how good you all are, right? X plus x equals, can I add that?
2x.
2x. Right? So that means that I have a bag of mangoes. I don't know how much the bag of mangoes is. I don't know how much mangoes in it. That is why it's x. So I have a bag with an unknown quantity of mangoes, but I have a next bag with the exact same quantity of mangoes. That is the only way I could add them. Yeah, that is the only way I could add them, right? Number 2. What about this? 2 multiply by x. Shreya, can I do this multiplication? Hey, Shreya bail out, yes? As soon as I ask you a question, I'm sure she might be just press a button wrong. Sydney, what will I get when I take 2 and multiply it by x?
2x.
Yes, 2x. All right. Number 3. All right. What if I have this? X plus y. All right, xy. Sarah, can I do that?
So it'll just stay as x plus y.
It will just stay as x plus y.
Oh, wait, x, y is multiplication.
Yes, xy is multiplication. Right? So these are the little things that we must know. I have a bag with an unknown quantity of mangoes. I have a different bag, but it have a different quantity of mangoes now. I don't know how much in the first bag, and I don't know how much in the second bag. So I can't just say that is just times 2. I can't just say that, because I don't know how much in each bag, but I know that they are different. So you can't just times 2, right? So you can't just multiply them by each other. But, of course, you can multiply them. X multiplied by y is just simply xy. Notice we didn't change nothing here, you know. This still means x multiplied by y, right? Similarly, over here, we didn't change nothing over here. This still means 2 multiplied by x. But why is it that we could write it glued together like that? Why? My students should know the answer for this. Why? Why it is that you could write these numbers together like that?
Yeah, because multiplication glues numbers together.
Like a boss. That's what I'm talking about.
Take off it as one number.
Yes, so multiplication, and this is especially for the new student who may not know, multiplication glues numbers together. Multiplication and division. So you could put and division here. And I'll show you the division one now. What this means, Sydney, is that when you multiply 2 times x is 2x, we could now treat that like if it's one number. Yeah, this xy, I could treat it like if it's one number. Multiplication glues numbers together, but addition and subtraction, as you could see, it separates numbers. This is the essence of BODMAS. This is why in BODMAS, you just had to do the multiplication first, because multiplication glues numbers together. 6 times 3, right? 6 threes, these are just the factors of 18. So 6 times 3 is really 18. It's really just one number. Yeah. So these are the factors you could see. So xy is the factors of x multiplied by y, right? Similarly, when you're dividing, right? I mean, you have x divided by x. Anybody want to tell me what is this?
1.
It's 1, right? X divided by x is 1. Because you could see that, well, it's the same number divided by itself. All right. What about number 6? What about x? No, what about 2x divided by x? Right? The x's here will cancel, and you will get 2. Did that stump you, Sarah?
No, sir.
So how
I didn't
come?
know I was giving somebody a chance. I thought it didn't want me.
I don't really have much people here, so anybody can answer anytime. And Joseph using a convenient microphone excuse to stay out of the conversation, right? But why? Why is it? Because imagine if you have 18 divided by 6. What is 18? 18 is 6 times 3, right? So I could put 3 times 6 over 6. So you can see it's the 6's that cancel in here. That is give you the 3. So similarly, the x's could cancel here. But what about if I have 2x all over y? What is that?
It'll just stay as is.
It will just stay as is. All right. What about this? X squared divided by x. Can I do that?
X.
All right. You know what? I feel like I'm going to start to call people names. Remember, x squared is really x times x over x. Cancels, x day. Yeah? What about this?
Yes, I say no.
All right. Yes, I say no. No, you cannot add those two things. It will just stay right how it is. You cannot add an x and an x squared. You don't know how much x is. And so therefore you could never know how much x squared going to be. You know? Because if like x is 5, for example, well, that means that 5 squared going to be 25. So these two different numbers, this is kind of like an x and a y situation. Yeah, these are two different numbers you're talking about here, right? So you could only add numbers of the same power. So for example, if I had, x plus x, well, yeah, these two have the same power. So that will give me 2x, right? I could also have, like, let me just say x squared plus x squared. Well, as long as they are the same number, I could add them to get 2x squared. Yeah. So these are exactly the same number, x squared and x squared. But these are not. Even though they have x in them, this is a x squared. This is a different number from this. Because this number could be 5, and this number going to end up being 25, So these two different things. So Sydney, you understand?
Yes, yes.
Right. So you cannot add those things. You could only add numbers, right? We could only add numbers that are exactly the same in polynomials, right? So numbers that are exactly the same, we could add. Maybe we could write that down, right? We can only add numbers that are exactly the same. Example, y plus y is 2y. Or you have q squared plus q squared will give me 2q squared. Or z to the 5th plus 2z to the 5th could give me 3z to the 5th. So even though this has a 2, it does contain the same number. And it contains the same number as the Z5 there. It's just telling me that it have 2 of them. Yeah, twice the same number. And so now when you add 1 time the same number to twice the same number, you'll get 3 times the same number. So this is kind of like saying 1x. This, if you're confused about this is just like saying 1x plus 2x will give you 3x. 1z squared plus 2z squared, z5 plus 2z5 will give you 3z. So it had 4 earlier. So we're going to do 4 questions.
Negative 4x, and then I do minus 7x, and
Right.
then negative 11.
So negative 8x plus 4x minus 7x. She did this first, which is 4 plus 4 minus 8. The signs are different, so you find the difference. You keep the sign of the larger number, and don't forget your x. I think that is where you was forgetting, Joseph. You forgot either the p's or the q's or something, right? And then you have the minus 7x. And well, now the signs are the same. And so when the signs are the same, you add them and you keep the sign. Minus 8y. And you could feel free to be wrong, Sydney. It's totally cool. I might trouble you a little bit, but you know how to study it. Yeah. But I could have do it a different way. I could have say, well, you know what? Look at this. This is minus 8 minus 2. Well, I know the signs are the same, so I could add them. I add and keep the sign. 8 and 2 is 10. So it could be minus 10y, right? Plus 4y. Right, so this is what the associative law does allow me to do. It does allow me to recognize things that I could add easy. And of course here the signs are different, so you could find the difference and keep the sign of the larger number. So this is where these rules come into play, right? So what do we have here? Minus 5y minus 3y cubed plus 41y. Notice I cannot add the y with the y cube. I can't do that, right? So that means that I could add the y with the y. So I have minus 5 here, and I have plus 41y here. So 41 minus 5 is 36, rightfully so. And then I'm left with this minus 3y cubed that I cannot do anything with. Of course, I could probably factorize this, but we're not talking about factorizing today, right? But yeah, I can't do anything with that in terms of algebra, so we'll just leave it just so. Excellent job. And Joseph, well, we have this one here, minus 11q plus 2q minus 41p. Joseph, notice that this is 41p. It's not q. So I actually cannot add this with anything else. You seeing that, Joseph? So that means that that 41p is going to be in my answer, right? And I just had to tackle these q's here now. Minus 11 plus 2. The signs are different, so I find the difference, 9q, and I keep the sign of the larger number, which is the negative. So the answer is, so you see how you get your negative 9 there. I don't know if you had known what to do with the 41, but this is the answer. The answer is actually negative 9q minus 41p. You understand that, Joseph? So we're talking about the same directed numbers business, but we're dealing with multiplication and division now. All right, and we'll just go through the rules of directed numbers for multiplication. I hate this word, boy, plication. It's so long and totish. Multiplication and division. And it's hard to write too. All of those vertical strokes. Multiplication and division, right? So the rules that we have to know with multiplication and division are simple. Right? If the signs are the same signs, well, then your answer is going to be positive. So therefore, well, example, you have the same signs. Let me just say negative 2 multiplied by negative 4. Well, you'll get same signs, they're both negative, so 4 2s are 8, you'll get positive 8, right? If you had a positive 2 multiplied by a positive 4, well, guess what? The signs are the same, so you will still end up with positive 8. Oops, why did I put 4 there? Right? This brings us to an interesting note about squares and square roots. Note that if I have 5 multiplied by 5, this is 5 squared, which will give me 25. Note, if I have negative 5 multiplied by negative 5, this could be seen as negative 5 squared, which will give me 25. Therefore, if I have the square root of 25, right? Let me see. Sydney, where's the square root of 25?
5.
Right. That is not the answer. That is not the correct answer. We're doing add maths now. This is the CSEC maths answer. Yeah. This is the... There we go. plus or minus 5. And this is why. You notice I get 25 for both of them. If I take 5 and multiply it by itself, I'll get 25. But if I take negative 5 and multiply it by itself, I'll still get 25. All right? So note, a square is a number multiplied by itself. That is why it is impossible to have the square root of a negative number. You could never have a negative number. The square root of a negative number does not exist. And the reason why is because in order for you to get the square in the first place, you had to multiply the same number by itself, which means both numbers would have to have the same signs, and so the answer would be positive. The only way for you to get a negative number inside of there is because of the rule number 2. Different signs. When you're multiplying or dividing different signs, your answer will be negative. So the only way you could get a negative 25 inside of here is if you multiply 5 multiplied by negative 5. That is the only way you'll get negative 25. These are not the same numbers. So this is not a square. And so therefore you cannot find the square root of that. A square is a number multiplied by itself. Sydney, did you know all this stuff before? Did you ever think about this before? In Form 2, Form 3, and things. So you did this stuff already, but you probably slipped your mind, right?
Yeah.
Well, this stuff is really important to remember for the multiplication of numbers. So once you had different signs, your answer going to be negative. The other example is like, let me just say if you have minus 10 divided by 2, right? That is equal to negative 5. The signs are different, so your answer going to be negative, right? Example, check this example. You have 10 divided by negative 2. Well, that is also negative 5, isn't it? So therefore, we could say that if I have the top number being negative, that is pretty much giving me the same answer as if I had the bottom number being negative. Because once one number is negative, that means the whole thing is negative. Now, to talk about multiplication and division, we're going to have to get into the laws of indices. And you'll see here that we have laws of indices. This is all of them that you need to know, and we will get into them now. But just basic, we'll just do the first couple of basic laws of indices first, right? Just the first couple of your basic laws of indices first. So, just the basics. And this is polynomials. And we're doing multiplication and division, right? So number 1, what do I get when I have x multiplied by x?
X squared.
X squared. So the next question is this. What about x multiplied by x squared? Yeah. X cubed. Okay? So you can see that we have the basic laws of indices here, where we basically add your indices, right? So that's the first law of indices that we're just gonna take a look at, where you're adding your indices. So 1 plus 2, x is equal to 3. So when you're multiplying, you add your indices, right? What about x squared multiplied by x cubed?
5.
5?
X to the power of 5.
Uh-huh. All right. X to the power of 2 plus 3, which is 5. No. You see where you do this here? Gosh, man. X to the power of 5. All right. So we can see the most basic laws of indices here. You could only add indices if the base numbers are the same. So what if I had x squared multiplied by y cubed? What'll I have there now? So I could write them glued together like this. But this means the same as this. Yes? All right. And then we just have other things too, like what is x squared divided by x? Sarah, I believe it's your turn again.
So x.
All right. So remember, x squared is x multiplied by itself twice. And so this x will cancel with one of these x's. But you can also use the laws of indices, which saying that when you are dividing, you minus your indices, which will give us x to the power of 1, right? So that was number 5. Sydney, I believe this one is yours, right? What about x cubed divided by x fourth? According to the laws of indices, this will be x to the 3 minus 4, which is x to the power of minus 1, right? But remember, this is equal to x multiplied by itself 3 times, all over x multiplied by itself 4 times. And so these will cancel with these, and you'll get 1 here, and you'll end up getting 1 over x, right? So therefore, x to the power of minus 1 is the same as saying 1 over x. Yeah. So we're starting to get into laws of indices realm here. So we're going to tackle more of the laws of indices just now, but let me get to the questions first, right? So same rule, we're doing 4 questions. We will do this one. Oh, I'll use the blue. We will do this one. We will do this one. We will do this one. And we will do this one. You have to do all 4, and you have to say done it when you're done it. Same rules apply. I'm gonna choose one person each, but of course you had to do all 4. Why is this on the screen? I hate Zoom, boy. Say done it when you're done it. And Sarah, give me number 1. Minus 5x multiplied by 3x gives me what?
Negative 15x squared.
Right, negative 15x squared. So you have x multiplied by x, negative 15x squared, and 5 3s are 15, right? This next one, we have negative 9x divided by negative 3y. So, Sydney, let me hear this one, right? The negatives will cancel out the negatives, right? This 3 will cancel out into this 9. So 3 into 3, 1, 3 into 9, 3. And so I will get 3x on top, and I will get a y underneath. Now, we do have to do a review of fractions. All right, we have laws of indices here. We do have to do a review of fractions. All right, I have a ton load of indices here, but we'll get to that. The hardest one for you, negative 36x squared y cubed divided by negative 6xy.
6xy squared.
That's the answer.
Yeah.
All right, now first of all, the negatives cancel off. All right, 6 into 6, 1. 6 into 36 is 6. X into x1, and well, this will cancel into one of these x's, so we'll get x here. This y will cancel into one of these y's, so we'll have y squared here, and so we get that answer there. And Joseph, the last one, 1 over x squared multiplied by x squared over 1, and so this will just cancel into this. All right, and we'll just get 1. Now, of course, you have to do the rest for homework. And before we talk about the laws of indices, I do want to talk a little bit about some fractions stuff, right? So just a little bit about some fractions, a little review. What is a half multiply by x?
X on 2.
Right, so this, when we are multiplying fractions, just for anybody who don't remember, the rules for multiplying fractions, you just multiply your numerators and you just multiply your denominators. So x times 1 is x, and x times 2, x is 2, right? But, and I could also write this, a half multiplied by x. I could also write it as this, a half x. Because a half x means a half multiplied by x. So I could write it like this, a half x. But I need to know that a half x is the same thing as x on 2. But look at this one. If I had 3 on 2 multiplied by x, what will that be? Now, we can see 3 on 2 multiplied by x. I could also write it like this. 3 on 2 multiplied by x. I could write it like that. But 3 on 2x means 3 on 2 multiplied by x. So you could do the 3 times x and then the 2 times 1. So the 3 times x will be 3x all over 2. The point about this is that the point about this is that when you see this, you are supposed to know that it is the same as this. Or when you see this one, you're supposed to be able to split it up like that. You're supposed to be able to also split it up like that. So, the third example, if I see something like this, PQ all over XY, this is a multiply. The numerator and the denominators are multiplied, right? So this could mean many, many things. I could say that this could be P over X multiplied by Q over Y. Because if I do the multiply, I'll get back this. I could also say, you know, it could be PQ over 1 multiplied by 1 over XY. Yeah. I could also say it's like that, because if I multiply this out, I will get back this. Comes the multi. Well, I have a question for you. I have here 6y divided by 3x. Where's 6? Remember, multiplication is glue numbers together, so this is one number. This 6 is with our y. So how it is that this 3 is with our x, this 6 is with our y, but I could still cancel the 3 with the 6. Even though I can't cancel the x with the y, I could still cancel the 3 with the 6. How is that possible? Because of the same rule for multiplication, that this is actually 6 times y all over, this is a multiply sign, all over 3 times x. And so I could split it up to say that this is 6 over 3 multiplied by y over x. And that is how the 3 and the 6 could cancel to give me what? 2y over x? But what about this one? What if I had 6 plus y all over 3 plus x?
Sweet.
Rules for fractions, for addition and subtraction. So check this out, and this will remain exactly how it is. 6 plus y all over 3 plus x. I can separate it, I can separate it. When I separate it, you know what it's gonna be? It's gonna be 6 over 3 plus x plus y over 3 plus x. That is, you know why I could make the separation? Here, if I had 1 over 5 plus 2 over 5.
You can add 1 and 2.
Right, so you add, so this is 1 plus 2 over the same denominator, and you get what I'm saying, Sydney?
Yeah.
This is 1 plus 2 over the same denominator. So imagine I had a situation where I was given this 1 plus 2 over some denominator, right? Well, I could then say, well, you know what? That plus there, meaning that this 1 is over this denominator, and this 2 is over this same denominator. So I could split it up like this. And that makes sense? I just went in the other direction, right? So another example of this would be if I had, say, P plus Q over Z. Well, these are two adding numbers that are over the same denominator. So I could say that this is P over Z plus Q over Z. Because look, this is a SCA rule. And with this SCA rule, I'm talking about standard 5 here. With this standard 5 rule, look what we could do with it. In fact, look on this side and see what we could do with it. Because 6 plus y over 3 plus x, I could see the 3 plus x as being one denominator. And so I could split it up, the 6 over 3 plus x plus the y over the 3 plus x. So Sydney, do you understand how I can make this separation? Now, why it is I can't just cancel the 3 with the 6? Because that 3 is not dividing the 6 alone, you know. That is 3 plus x, it dividing the 6. But that 3 plus x is also dividing the y. But that is not the case over here. Over here, I could divide, you could see how this split up. So that 3 could get split up with the 6. And, you know, because it's multiply. And multiplication glues numbers together. Addition separates numbers. Sydney, is your brain starting to swell inside of your head right now?
Yeah. Yes, that's 100%.
All right, because we are going to be doing, you see, these things I talk about, these basic things with fractions here, they're super important. You're going to see them. You know you're going to bounce up a situation like this, and you're going to wonder if you could cancel the 3 with the 6. You know that's going to happen. Yeah? So it's all about knowing these laws of indices here. The last one is really interesting though. It have so would anything to the power of 0 is 1. And of course, there's the other rule that anything to the power of 1 is itself. And in the CSEC maths class, when we did laws of indices, I asked you to prove all of them. So you are supposed to be able to prove all of them. And Shreya, you did law 6 with me already back in July. I don't know if you was in my maths class in July. And?
No, I joined in September.
Oh, for real? You joined my CSEC maths class in September? We did this. And this is a real interesting one. Because what this really says, look at this n number here. And look at this n number here. Right? So rule number 6. This one here. So let me just talk about rule number 5 just a little bit first. It's an easy rule, right? It says that if I have x to the 2 and all of that is raised to the 3, then that will be x to the 2 times 3, which is x to the 2 3s are 6, right? Now this becomes an interesting rule when you add fractions, right? So when you add fractions, and I'll do the next example here. For example, if I have x to the half times 3, right? That is equal to x to the half times 3. Yeah? So therefore, that is equal to x to the 3 on 2. Remember, multiplication is commutative. So therefore, x to the half multiplied by 3 is the same as x to the 3 multiplied by a half, which is the same as x to the 3 with the half on the outside. And therefore, x to the power of a half with the 3 on the outside is the same thing as x cubed with the half on the outside. Is that a to the m over n is equal to, look at that. If you have x to the power of a half, that is the square root of x. So the square root of a number is actually that number to the power of a half. Right? Similarly, if I have x to the power of a third, that would be the cube root of x. So the denominator of the fraction is the root that you're dealing with. So we could have the situation where we have x to the 2 on 3. Now, x to the 2 on 3, we could say to be x to the third, and we could put the 2 outside. And we know x to the third is the cube root of x. And the cube root of x, we could have all squared there, because the 2 on the outside. But remember, x to the 2 on 3 could also be seen as x squared with the cube, with the third on the outside, because multiplication is commutative, right? So that means that I now have that x squared, and the cube is on the outside. And I don't know how mind-blowing this rule is, but therefore this rule states that you could have the cube root of x squared, and that is going to be the same thing as if you have the cube root of x all squared. That is what, and I feel sure. Joseph, put your answer in the chat for this one, please. And let's just tackle this one. How about Shreya first this time? Shreya, you want to give me this one? All right, so this here is just simply 2 to the power of, this is a multiply. So when you multiply, you add in your indices. So this is 6 plus minus 4, right? So that will give me 2 to the power of 6 minus 4 is 2, which is just simply 2 squared, 4. Right, it would be the square root of 9, it's true, right? It have another way you could work it out as well, right? So you have 9, let me just use the white for this one. 9 to the power of a half times 3 squared. Yes, that is the square root of 9 times 3 squared, which is 9, right? So we have the square root of 9, which is 3 times 9, which is 27, right? Another way we could work it out is 9 to the half times 3 squared. 9 is 3 squared, right? So imagine 3 squared, that is 9. That's going to be to the power of a half. And then you have times 3 squared there, right? So that means that I'll have 3 to the 2 multiplied by a half. That is 2 on 2. 2 multiplied by a half, we'll get 2 on 2 multiplied by 3 squared, which is 3 to the 1 multiplied by 3 squared, which gives us 3 to the cubed, which is 27. So nice. Sydney, you can give me this one. So this is 3 to the power of 3 minus 5, which is 3 to the power of minus 2. How will you finish it? Well, 3 to the power of minus 2 is 1 over 3 squared, which means the answer is actually 1 over 9. See that? Give me this one, please. What you got for that? 4 to the half divided by 16 to the quarter. Yes, Joseph, this time you got the hardest one of 2. So I could say that 4 is actually 2 squared, right? And that is to the power of a half. And that'll be divided by 16. There's 2 2s are 4 2s are 8 2s are 16. So 16 is 2 to the power of 4. And that is to the power of a quarter. And so therefore this will be 2 to the 2 multiplied by a half is 2 on 2, all over 2 to the 4 multiplied by a quarter is 4 on 4. And that will give me 2 to the power of 1 divided by 2 to the power of 1, which is 1. Excellent job. You have more laws of indices questions that you have to finish here. You have more laws of indices questions that you have. Slide 15, right? So your homework for next week, and I know it seems like a lot, but don't worry, it's not a lot. You could probably get this done in half hour or maybe 35 minutes, right? The homework is complete slides 1 to 15. What do I mean by complete? That is, all right, read, make notes, and finish the questions. Any questions at all? You should have been in my Form 1 to 3 class. My Form 1 to 3 class is all kind of fun and games, but my Form 4 and 5 classes is straight down to business. No fun and games here, right? So from the next class, we're going to get into polynomials. We still are quadratic equations. This topic is the same as your CSEC maths. So the quadratics that we do in AdMaths is pretty, and you can see what's going on here. The quadratics we do in AdMaths is pretty much the same as the quadratics that we do in CSEC maths, but it does have just a little more on the algebra side, right? So quadratics is one of the first things what we're gonna do, but before we do quadratics actually, so I might put this one over here. Before we do quadratics, we're gonna do something called the remainder and factor theorem. So this might be our third class. And this is what the remainder and factor theorem looks like. As you can see, it's a lot of algebra. It's just algebra. Algebra, algebra, more algebra. Look, I'm dead with algebra in this class. But you know, what's the cool thing about AdMaths? Like, what do you think is the difference, apart from the algebra? The difference between CSEC level maths and AdMaths. What do you think is the difference? Right? We're talking about linear math. For example, right? Let me just say you have your profit over time. You're working, you're selling bourbon biscuits, and you want to make a profit over time, you know, and that profit, your profit could be probably given by an equation, something like the amount of bourbon biscuits you sell, right, minus how much the cost that you pay for it, whatever. This is a linear equation. If you plot this, your profit going to come out looking like this, you know, where, you know, the more that you sell is the more profit you make, and everything nice and simple. So that is what CSEC maths is about. The problem is life does not work like this. Life will work like this. And what you'll find is that your profit's going to be changing. Maybe this period you're going to end up dipping, you know, maybe. And if you ever do, you know, you ever look at things like Forex trading or Bitcoin, you'll see that they're talking about this kind of stuff a lot. that, you know, the price of Bitcoin might go up and everybody go get all excited, but then all of a sudden it go down, and then all of a sudden it going all the way down, and then it go just crash. You know, this is what life is really like. So when we're talking about add maths, what we actually talking about here is the mathematics of change. Everything in life is change. Nothing in life is constant like this. Everything in life has to do with change. And so mathematics, add maths, is the mathematics of change. And that is when we get into something called calculus. Calculus is when we do dy over dx and that kind of thing. This is actually the mathematics of change. Remember, I just keep saying maths is a language, and that the grammar for that language is algebra. So add maths, you all are actually going to get very, very strong at speaking the language of mathematics. So that's it for the first add maths class.